Okay, this crude picture depicts a mass suspended from a spring, and we'll assume there's something solid up here to support the mass. Equilibrium position, we're going to set y equal to 0 in equilibrium. We set y equals 0 any place we want to, but it's a whole lot simpler to set y equal to 0 at the equilibrium position. Initial position is going to be y equals y sub 0. Now you know enough differential equations that you'd actually solve the equation for the motion of this thing. We'll save that for later. Okay. So we release this thing from rest at y equals y naught at this position. So just two fairly simple questions, and then we'll ask some harder ones. Okay. What's the speed when it hits the equilibrium position? And what's the maximum value of y of t? Y being the y-axis being in this direction as I depicted it. See what you can do. Use energy, because energy is the only way you have of analyzing this. And I guess I'll tell you, although you should be able to integrate and derive this and work on that. And maybe you can. If you can tell me why elastic potential energy is 1/2 ky squared, please do that too. Otherwise, you can just use it. And I really want to focus on how energy considerations allow you to answer these two things. And the one thing that doesn't help remotely is equations of uniformly accelerated motion, because the acceleration is not uniform. The further we are from equilibrium, the more force is being exerted on the mass by the spring. Okay. So the acceleration is absolutely not constant. So the equation of uniformly accelerated motion assume uniform acceleration, which assumes uniform net force if you're talking about a constant mass. Okay, so forget about the equations of uniformly accelerated motion. They're worthless here. Okay, first thing I'm going to do is going to look at this. If the mass has little wheels on it, maybe, or the surface is completely frictionless, but where we have negligible friction. Okay. So here's going to be the equilibrium position. And we're going to pull it up at some position X. Yeah, I'm going to call it X. Okay, equilibrium position is X naught, here is position X. So when we're out here, the potential energy is 1/2 kx squared. Releasing it from rest. So what's the total energy? Total energy at this point. I'm going to call this X sub I, or X initial. I don't want to use X as a variable. Okay, total energy I'll use the textbook's notation. U for potential energy, K for kinetic energy. This is a capital K. To distinguish it from little k, I'm going to put little feet on it. Things got feet in all directions. And what's the kinetic energy at this point? It's zero. So your total energy is this, right? Okay. Now I ask how fast it's going at equilibrium. Well, how do you use energy considerations to figure that out? Well, can you answer what the total energy would be at the equilibrium position and why? Actually, I'll say it the way that we've developed it. And you go back to review what that is. Change in K plus a change in U, change in kinetic plus a change in potential energy is zero. So that kinetic plus potential energy is constant. Since it's equal to this at one known point, it's equal to that everywhere. And by everywhere, I mean everywhere within the system, as long as our assumption that the net force is negative kx is valid. Okay. Now you put some sandpaper down on the surface here, or put something for this thing to run into. That's all going to change, but we're assuming that's not the case. Okay. In the real world, of course, you are dissipating energy, and the amplitude of this vibration decreases. Okay. So you have to understand this, because you're going to have to apply this idea in a variety of other situations, in the homework, on tests, throughout the rest of the course. Okay. Make sure we understand the logic of this argument and understand the principle. If the net force is conservative, then the total energy doesn't change. Okay, now. What's the velocity at equilibrium? Well, And I wrote you there, should have gone ahead and written out. They must have a lot of room, but I squeezed it in. 1/2 mv squared plus 1/2 kx squared, right? The equilibrium, x equals 0. So 1/2 mv squared plus 0 equals 1/2 kxi squared. So that p is the square root of kxi squared over m. You know, multiply 3 by 2, the 1/2 go away, divide by m, and then solve for b. Now, one thing I think everybody left off is a plus and minus. And some people might have had that numerator wrong, might have had an m in the numerator or something like that. So don't let that happen. Just do your algebra carefully and correctly, because otherwise you're doing it like I do, and it causes me all kinds of problems. Don't cause yourself the kind of problems I cause myself. Okay. Don't be careless, in other words. Simple enough. What about the second question? Well, now analogy to the second question would be, since our x-axis is presumably in this direction, what's the least value of x that we get? Okay. So the minimum what's the minimum value of x? How are we going to approach that? Okay, so the suggestion I got, well, let's solve for x instead of b. Perfectly good solution, perfectly good suggestion, and it actually takes us a step further than I was going to go with this step, but we're going to do it because we get to the same place, and the reason is still more difficult. Okay. Now that's going to be 1/2 mv squared plus 1/2 kx squared equals 1/2 kxi squared. And we want to solve for x. Well, it's real easy to solve for x. All the 1/2s multiply out. We'll multiply everything by 2. And we're going to get x equals plus or minus square root of kxi squared minus m v squared over k. Now, the reason I kind of like doing this, the reason is a little more subtle. This is your fundamental relationship here. You know, usually this xi squared is going to be a capital A. I don't want to make it a capital A at this point because in a minute, I'm going to kick this thing before it starts. I'm not going to release it from rest. And A stands for the amplitude of the oscillation, which is your maximum displacement from equilibrium, okay? So ordinarily be 1/2 Ka squared. That's the energy relationship for any simple harmonic motion. Right now, I'm using xi squared for reasons that might or might not be apparent, but they should become apparent. Okay, so we got this. how are we going to determine what the maximum value of X would be? Can you look at that expression and see what it is that would vary within that expression, and how do those things vary? Okay, I got one answer to my question of what has to happen here in order for X to be as big as possible. Okay, it was a good answer. There are two answers. They're both good. Okay, one of them pretty obvious. Now there's an assumption involved. After you pass equilibrium, the restoring force is going to be in this direction, so that the thing will eventually come to rest. And at that point, V is zero, right? Okay. So you could set V equal to zero, and that's going to give you the max. Okay, that's really good. We'll write that out in a minute. And you know, when it is, when V is zero, what do you get? What's the square root plus or minus the square root of kxi squared over k? Well, you divide the k out, and you get the square root plus or minus the square root of xi squared, right? And which is what? Plus or minus xi. Okay. So V equals zero, you get plus or minus xi, and that's just immediate. Which means what? In terms of this motion, it means if it's released from rest here, and this is your net force, it's going to be at negative xi here. Anytime V is zero, it's going to be at either xi or negative xi. Well, that makes perfect sense. It's going to oscillate over to here, back to here, over to here, back to here. It's not losing any energy. It's going to keep going the same distance. Okay. So in the ideal case, it'll hit position plus xi an infinite number of times, hit minus xi an infinite number of times. And in the process, it's going to have a sine wave type motion, which you could easily solve, be an easy differential equations problem. You'll have that. So, okay, well, the other answer is, well, when somebody said, well, this can't be negative. Okay. Look, if your velocity is this, and you plug this in here, square it, you're going to get kxi squared over m, and multiply that by m, you're going to have kxi squared. You're going to have kxi squared minus kxi squared, which gives you zero, right? Okay. Which means that V can't be bigger than this. If V was bigger than this, your potential energy is never negative. Your kinetic energy would be greater than the total energy, and your energy can't be greater than the total energy. It violate energy conservation. So I said that kind of quick. If you really want to analyze what I said, go back to my words. I think they're right. Okay, so anyhow, that's kind of interesting. Or if you solve this for when this is negative, you find that V is bigger than this. That'd be your solution. Just do the algebras. Simple algebra 2. Can't write in these part without wanting to write them 1/2. Right here we have this. V equals 0, X equals plus or minus xi. It could be obvious looking at this, that the smaller v is got stuff writing down nonsensical words here. But the smaller v is makes this greater, right? This expression comes this xi squared, which is the greatest possible value you can have. This thing takes its extreme value for v equals 0, and one of the extreme values gives you position on this side. The other extreme value gives you a position on this side. So I maybe went a little further than we really need to go with looking at that expression, but you need to be able to interpret the expressions you get. Okay. And there are various ways of looking at it, and that's one very valid way to look at it. And there are others. We don't want to go into all that detail. Okay, so there we have it. Now, I want to pose the question. Give thing of speed vi, position xi. What are our answers to the same questions we posed here? So we pick the thing, one direction or another, doesn't matter. It's going to turn out that it doesn't matter. What's going to happen? Okay, so the question is, what changes? And in discussion, we said, well, the kinetic energy changes. And I responded, well, yeah, the kinetic energy where? Because they're placed with kinetic energy 0. That doesn't change. Okay. But intuitively, if you give the thing a kick outward, stopping point's going to be further out, right? Okay, so you have that intuition. And if it's further out here, then it's probably going to be further in here. If you kick it in this direction, well, it's probably going to go further here, which means it'll come further out there, right? That's intuitive. We want to do this in terms of energy conservation, so we're sure we don't screw it up. So yes, the kinetic energy changes, the position at which the kinetic energy becomes zero changes. You could make that jump, but the thing you really need to do, we finally got to it, after a little discussion, somebody said, well, the total energy changes, and that's the key. Okay. Because we're talking about energy conservation. So can you write out the expression for the total energy now? What's the expression for the total energy? Recording is supposed to stop. Can you read that? I just wrote 1/2 kxi squared plus 1/2 mvi squared. Okay. Now, when I looked around, I saw you writing down 1/2 mv squared and 1/2 kx squared. I didn't see the subscript I on some of what you wrote. I saw it in some. Okay. If you don't have a subscript I, you're not talking about what happens at that initial point, right? Because that's very specific. So you got to understand that. Now, what's the maximum speed and where does it occur? What are they string positions? And what's the velocity as a function of position? What's your kinetic energy as a function of x? To cut through all this, of course, we have to write down the expression for the total energy. Okay, well, we've got it. There it is. Okay. So we have to use this expression to answer these questions. So how do we use this expression to figure the maximum speed? How's this expression going to be related to the maximum? Well, this is your total energy. I mean, I probably should have shown you this step. At any point, your energy is this. What's U and what's K? Well, at this point, U is this and K is this. At any point, you have this. Because V and X vary. V sub I and X sub I don't vary. So if you're trying to deal with just this formula for the total energy, you're not going to get very far. You got to see what it's equal to, okay? And I probably should have done that step for you because that's not something you're going to naturally see. You're going to be thinking in terms of equations and formulas and stuff. And it takes a while to get used to thinking in terms of energy. So probably wasted 5 minutes of your life there, but there we have it. Got it? Now, can you answer what's the speed, maximum speed, and at what position does it occur? Remember that your I was in the middle of saying something, and Zoom actually did what I would have wanted it to do if I wasn't used to what it is doing. Anyhow, again, trying to figure what the maximum speed is and where does it occur. Things on this side of the equation can change. Things on this side of the equation aren't going to change, right? So when these things change, what change gives you the maximum speed? Okay. It always amazes me how long that takes. It's very simple once you know what to look at. Okay. We kind of saw an example before, but it's new and we're still processing it, because you want to process it a lot between now and next time. You want to do some problems, we have to apply this thinking. So the thinking is simple. How do you get the maximum value of V? Well, use the minimum value of X. Okay, you got a sum of two things here that's always equal to the same thing. If one of them gets big, the other gets small. The bigger one gets, the smaller the other one gets. They're both positive, so neither one of them can get any bigger than what's on the right-hand side. That's your maximum, right? Maximum total energy. Does that make sense? So again, say it again. You got two positive quantities because you got squares here, right? And your constants are positive. So you got two squares that add up to some fixed number. Okay. Well, if one of the squares is bigger, the other is smaller, and vice versa. And neither one can be bigger than this. Because if it is, the other isn't negative, then this side's bigger than this side. It's not going to happen. You really want to understand that because you have to apply it. You have to think it. It has to become automatic. It's not a difficult concept, but not probably one that you're used to thinking in terms of. Okay, so we have this. So, well, where does the maximum speed occur? I should say we should minimize X squared, okay? Be more technically correct. And now I can say X squared can be 0, but it can't be less. Okay. So V would equal square root of KXI squared over M minus VI squared. Plus VI squared. That minus is bothering me for good reason. It's plus. I don't use a plus or minus here. Since we're trying to find the maximum of V, which is a scalar product, officially V can't be positive, and V has to be non-negative because it's a magnitude of a vector, but we kind of gloss that over. Okay. So extreme velocity is plus or minus V max. Okay. Well, can you use similar reasoning to figure out the extreme positions? Okay, so if you want to maximize X, you got to minimize V, right? So V is 0. So then you get XI squared plus 1/2 MVS squared over K. Everybody get that? Did the arithmetic right? That's what you would have gotten. Probably unreadable. That's a 2 there. These really smart. Okay. Their extreme positions are plus or minus that. Now notice if VI is 0, what do you get? Wait a minute. Yeah. Sorry, if VI equals 0, what do you get? You get XI. X max is the square root of XI squared, which is just XI. Okay. And the extreme values of X are plus or minus X max. As could have said, similar to what we said here, I'm not going to write it out. And of course, if Xi is 0, then it's not going anywhere unless you give it a velocity, right? So if Xi is 0, then your maximum velocity will just be VI because that's what occurs at the equilibrium position. And that has to be your maximum because if you move away from equilibrium, the spring force is going to fight you whichever direction you're going. And the spring force is going to pull you back. It's going to try to pull you back towards the equilibrium position, okay? So it all comes out full circle. Okay, since you all have differential equations, I'm going to just give you a little addendum here. All this can be derived very easily. using one of the simplest of the differential equations that you learn to solve. And you can even show somebody these solutions after a semester of calculus. They'll need a differential equation. It's very simple. F net is equal to negative kx. Well, F net is equal to MA, so MA is equal to negative kx. The A equals negative K over M times X. But of course, A is just second derivative of X with respect to time. And that's a very simple differential equation. You could get someone to solve it if you let X equal e to the I R, okay? Or e to the lambda I. I like that better. You might use IR in differential equations. You'd use lambda I if you were thinking linear algebra and eigenvalues and stuff. Anyhow, and it's not lambda I, I'm thinking ahead, it's lambda T. Okay. Then what you get is you get lambda squared equals negative K over M. And this is square root of K over M. Negative 5. And I'm swapping this all over the place. You could let X equal A e to the lambda T and fill in the blanks. And you can combine these terms with arbitrary constants. And I wrote it out stupidly again. I'm going to make it C cosine of this plus D times I sine of this. And now using the combination of angles formulas, I can combine the C and the D into an A with a phase shift phi. You saw that in differential equations, didn't you? Maybe not. But anyhow, we'll do this second semester when it becomes important. Okay. I mean, it's important already because that's your general equation of simple harmonic motion. And from this, you can find the velocity function. You're going to get a square root of K over M when you take the derivative, right? And the acceleration function, you get another square root of K over M. So you got a square root of K over M. And what square roots of K over M occur? Well, there. Okay. And it turns out the square root of K over M, you call it omega because it's just an angular velocity on a reference circle. Relates right back to what we did first day, angular velocity. Okay. We put it together, just something to look forward to, but everything that we got here, we can get here. Because we've got our position function, we get our velocity function and our acceleration function, meaning we can get our kinetic energy function, our potential energy function, and everything else. Okay.